Hi gentlemen, these will be your notes for Unit 3, Day 3 of Pre-Calculus. If you would like to see the warm-up, review question, or any of the homework questions we covered today in class, just look at the finished notes in today's module. So today we're going to continue our discussion about quadratic functions, and we're going to use quadratic functions to be able to model a problem and to solve for given information based on our quadratic module. We will be able to do this by hand and also using Desmos. So let's start by looking at one that we can do by hand. So a farmer has 2,000 yards of fence to enclose a rectangular field. What are the dimensions of the rectangle that encloses the most area? When I'm teaching this in Algebra 1, I teach my students to read the problem twice and then to pause and think about what do they know about the problem? What things do they still need in order to solve the problem? Is there a problem that they've done that looked like this problem? Have they done one before? What strategies or methods could they use to solve the problem? And then to get started on it after they've kind of thought through a process that might make sense to help them. So a farmer has 2,000 yards of fence to enclose a rectangular field. What are the dimensions of that rectangle that encloses the most area? So I always tell them that if you can draw a picture, draw it. So since it's a rectangular field, that means I can draw a rectangle. And then I know that he has 2,000 yards of fence to enclose that. Well, 2,000 yards of fence means that the perimeter of my rectangle can be 2,000. And that's all I know. I don't know what the side lengths are, so I'm going to call them X and Y. And I know that the perimeter of my rectangle would be 2x plus 2y, because x plus y plus y. And since he has 2,000 yards of fence, then I know that the perimeter is going to be 2,000 equals 2x plus 2y. What he wants to happen is he wants to maximize the area. Well, the area of that rectangle is going to be x times y, and I'm trying to maximize this. Well, I have two equations right now, and they both have an x and a y in them. So what I'm going to do is I'm going to take that first equation and solve it for either x or solve it for y. I'm going to solve it for y because that's what we normally do. So I'm going to subtract 2x from both sides. And I have negative 2x plus 2,000 equals 2y. And then I'm going to divide both sides by 2. And so now I have negative x plus 1,000 is y. I can now use that value for my y, negative x plus 1,000, and I can plug it back into the area formula. And now my area formula is x times negative x plus 1,000. And if I distribute that out, I have my area is negative x squared plus 1,000, x. Now, if you remember last class, we talked about quadratic functions, and those were functions that had the x squared. And when you graph them, they make parabolas. And this is a negative x squared, so it's going to be a concave down parabola. And we talked about how to find the maximum or minimum value of that function. Well, since it's concave down, it's a sad parabola, its maximum value is going to be at the vertex. And we talked about how to find the vertex last class. So since the area formula is a quadratic formula, to maximize the area, we want to know what the vertex is of that parabola, and then that's going to allow us to maximize the area. So our vertex is going to be the opposite of b over 2a is going to give us the x-coordinate. So my x-coordinate is going to be the opposite of 1,000 over 2 times negative 1, which is going to be 500. So the x-coordinate in this problem is going to be 500 for the vertex, and then the y-coordinate is going to represent what the maximum area actually is. So my y-coordinate, or my a, is going to be negative times 500 squared plus 1,000 times 500. And that's going to generate the maximum area for this box. So if I do this, I'm going to go on Desmos and calculate this. So I'm going to take negative and then 500 squared and then plus 1,000 times 500. And I get 2,500. So the maximum area that the farmer could enclose using 2,000 yards of fencing is 2,500 yards squared, or square yards. And there we go. Or if we wanted to, we could have graphed our original parabola. So negative x squared plus 1,000x. Oops. And we want to know the maximum on this guy. So if we scroll up, and here we can start seeing the parabola. So we're going to go all the way up, all the way up, all the way up. And notice this parabola goes up really high, and we're going to have to go all the way up to 2,500. And then if we go all the way up, notice that's exactly what we got for our vertex. So 500 would be the x-coordinate that we want, and then the y-coordinate, or which would represent the area in this case, would be 250,000. So we did it right. All right, so now let's look at the next problem. The Golden Gate Bridge, which is a suspension bridge in San Francisco, is 700. It has two 746 tall towers that are 4,200 feet apart. The bridge is suspended from two huge cables, each of which is more than 3 feet in diameter. So the thickness of those cables that are going through the Golden Gate Bridge are more than 3 feet in diameter. The road that goes through the Golden Gate Bridge, so it has a walking path and then both-way traffic, is 90 feet wide, and the road is 220 feet above the water. The cables kind of form a parabola in shape, and they touch the road surface at the center of the bridge. So where they touch right here would be the center of the bridge. We want to find the height of the cable that's above the road at a distance of 1,000 feet from the center. So if I go out 1,000 feet in either direction, I want to know what would be the height of the cable at each of those points. So that's what I'm trying to figure out in this problem. So again, read it twice. The Golden Gate Bridge, which is a suspension bridge in San Francisco, it's 740. It has two towers that are each 746 feet tall. So all the way to the water is 746. And I think it means that it goes underneath the water as well. So those are 746, or maybe it just means to the water, feet tall. And then they are 4,200 feet apart. So this distance right here, total, is 4,200. So that's going to be that distance between the two towers of the bridge. And they are 220 feet above the water. So this distance right here. So no, the roadway is 220 feet. So each of these, this distance right here and that distance right there is 220 feet. Okay, well, if that's 220 feet, what's this distance and this distance going to be then? Well, if the whole height, and I'm assuming that they mean to the water, which doesn't necessarily make sense, but we'll go with it, is going to be 746 minus 220, which is 62. So this height right here is 526, and this height right here is 526. Okay, so in order to do this, we're going to have to somehow put the Golden Gate Bridge on a graph. So let's put it on a graph. And you can kind of decide where you want to put it. I'm going to put the center right here at 0, 0. We could have put it anywhere we wanted to, but we could put the center there, and we could go out this way and go out this way. And to go out in both directions, well, if the whole span is 420, then go out each direction 2,100. So I could go out 2,100 in each direction. This is just one way of doing it. So I could go out 2,100 and 2,100. And then these 2 points here would be, I went out negative 2,100 in this direction, and I went out positive 2,100 in this direction. And then I went up 526 feet for each of those heights. So that's 526. This is 526. And then that's the point 0, 0. That's one way to think through the problem. Now that I have 3 points on that parabola, I can write an equation for the parabola. So remember, to write an equation for the parabola, it'd be y minus k equals a times x minus h squared. Well, the way that I wrote it, I made the vertex at the point 0, 0. So this is going to be y minus 0 equals a times x minus 0 squared. So this is y equals a times x squared. Well, now we can use one of the points. So I'm just going to use the point 2100, 526 as a point. So 526 equals 2100 squared times a. So I'm going to pull up Desmos again. Well, actually, I don't have to. I can just say that a is 526 over 2100 squared. So the equation for my parabola could be y equals 526 over 2100 squared times x squared. Now they're asking, find the height of a cable, find the height of the cable if I go out 1,000 feet. So if I go out 1,000 feet instead of 2,100 feet, then this would be the point 1,000 or negative 1,000 y, and this would be the point 1,000 y. So I'm trying to figure out the y if the x value is 1,000. So I'm going to plug in 1,000 for x. So y is going to equal 526 over 2,100 squared times 1,000 squared. Now I'm going to use Desmos. So I'm going to pull up Desmos. And so let's do 526 divided by 2,100 squared, and then times 1,000 squared. And then it looks like the height of the cable at that point is going to be 119.27 feet. And so that's one way of thinking through that problem. All right. So now we're going to use Desmos to be able to solve some quadratic model problems. So the data in Table 8 represents the average annual expenditures for consumers of various ages in the year 2016. So notice you have the ages between 21.4 to 74.3, and how much do they spend on average in thousands of dollars. So if you were 21 years old or thereabouts in the year 2016, then your average annual expenses were about $34,000. If you were 50 years old, then your average annual expenditures or your expenses were about $71,000. And then if you were about 74, 75 years old, it was about $45,000. So we're going to draw a scatter plot of this data, treating age as the independent variable. So that means that's going to be our x value. And the y value, which is our dependent variable, will be the average annual expenditures. So we're going to use Desmos to make that scatter plot. And then we're going to use Desmos to create a quadratic equation of best fit. So like we did with our linear equations, I'm going to show you how to do that with a quadratic equation. And then we're going to use that model that we get from Desmos to approximate the age at which the expenditures is the biggest, which if this is going to be a quadratic model, that would be at the vertex. And we want to figure out the highest average annual expenditure. And then we're going to draw the quadratic functions of best fit on our scatter plot. So let's do this on Desmos. So if you guys remember, on Desmos, if we did this, we could create a table. And then in our table, we have 21.4 and 34.4. And this is in thousands. And then we have 29.6. And we have 52.8. And then we have 39.5. And we have 66.4. And we have 49.5. And 71.2. 59.4. And 61.3. Oops. 59.4. And 61.3. And we have 68.9 and 50.9. And then we have 74.3 and 45.8. So there's my scatter plot. Hope we're still back in the I guess if I hit home, it'll take me back to the normal looking one. So here we go. So if you look at, they kind of are looking like a parabola. So do you guys remember how we used our Desmos last class or a couple classes ago to create a line of best fit. So to create a parabola of best fit, we're going to do something very similar. So we're going to use the y, and then instead of using the equal, we're going to use the approximate. So remember, that's down at the bottom, a couple over from that blue arrow. So there's the approximate. And then we can do, remember, it's ax squared plus bx plus c. So we can do this should be y1. Sorry, y1, and then a, and then we're going to do x1 squared, and then plus b, remember it's ax squared plus bx plus c, so that's going to be b, and then we're going to do another x1, and then plus c. So look at that. So Desmos will create a parabola of best fit, so a parabola that will go through the majority of those points. And so now Desmos is saying that our parabola of best fit is going to be a, and then y is approximately, the a is negative 0.0424905, and then we're going to have x squared, then plus b, our b is 4.20562x, and then plus c, and our c is negative 34.9639. So that's the equation for our parabola of best fit. And that's just from using Desmos. So we got our quadratic function of best fit. So now we want to approximate the age at which the expenditures are the greatest. So the expenditures are going to be the greatest at the vertex. So if I just pick that vertex on my parabola of best fit, the expenditures look to be the greatest. It would be $69,000. And that occurs at about 49 years of age. So 49.489 years of age look to be the greatest. Now notice on our real parabola, we actually had a value of 71,000. So you could also say that not using the parabola of best fit, but using the actual data, it happens at 49.5 years, which is very close to what our parabola of best fit gave us. To approximate the highest average annual expenditure. So the highest average annual expenditure is about, sorry, I lost my parabola vertex when I did that. So there it is. According to this would be 69,100. So $69,102 would be the highest, according to our parabola of best fit, annual expenditure, and that occurred when you were about 49.489 years of age. Use the graphing utility to draw the quadratic function of best fit. So we already did that on Desmos. So again, that's how we can use Desmos to plot points and create a quadratic function of best fit. So gentlemen, if you have any questions from today,